We're going to talk about multi-core programming concepts and tools. And these slides are adopted from Intel training materials. Here's a picture illustrating the evolution of multi-core technology. At early days, a microprocessor has only one core with improved performance by introducing this thread-level parallelism, instruction-level parallelism, and data parallelism. As the processor frequency goes higher and higher, it becomes increasingly difficult to keep pushing the limit of the frequency because the power consumption. So the trend is to have multi-cores in modern processors. And this trend is also apparent in the embedded processors. Traditionally, we think that embedded processors are low computation power, can be very simple, but as the increasing need in many of the embedded devices, for example, your smartphones, you can do a lot of things that you can do on the desktop in the early days. So a lot of computing power is needed in embedded systems. So that's why it's not surprising to see many new embedded processors have multi-cores. So you can easily find Atom processors have multi-cores, and in your cell phone, chances are, if you're using a recent smartphone, your phone is multi-core based, 2-core, even 4-core. So that's the trend of the processor architecture. And we're going to next introduce the concepts related to multi-core programming. We're going to start with a thread. A thread is a single sequence flow of control within a program. It's different from a process, which is a much larger entity than a thread. Essentially, a thread is a sequence of instructions that is executed. You may have a single-threaded program, but also, and oftentimes, you have a multi-threaded program for improved response time and throughput. Why do we use threads? There are many benefits. Some of them are, for example, increased performance. And also, because of multiple threads, you can better utilize the resource. Some threads can be doing computation. Some threads can be doing data access or I/O operations. And also, it improves efficient data sharing. Traditionally, if you want to share data across processes, you can use shared memory, you can use inter-process communication. But with threads, these threads, because they are within the same process context, so they can share data much more efficiently. The risk of using these threads, because the way people design applications, design programs, they are used to serial programs. So when you have multiple threads, and you're going to deal with a lot of challenges, including data races, where you may end up having incoherent data on different threads if you do not deal with carefully. Also, you may have the risk of deadlock the multiple threads, and the code is certainly more complex. Also, there are portability issues because different platforms, for example, Windows and Linux, provide different multi-threading programming libraries. So you have to consider how to design your program to be portable. And also, there are increasing difficulties in testing and debugging because you have multiple threads running concurrently. A process is a larger concept in modern operating systems. Processes have two roles: resource holder and execution unit. It is the main thread that initialized the process and began execution of the instructions. Essentially, when you type a command in Linux, the shell will start that command in the separate process. It essentially will initialize all the environment variables, allocate necessary resources for the program to continue. Processes and threads are different. Process has the main thread that initializes the process and begins the execution, and after that, any thread can be created within the process. These created threads will have their own stack, but they will also have shared data and code segment with other threads created within the same process. The differences has many aspects. Here's a table summarized the differences between threads and processes. In terms of the address space, a process has its own address space, which operating system protects. By address space, we refer to the code space, data segment, code segment, etc. Whereas a thread shares the process address space with other threads. And that's the main reason the data sharing becomes much easier, more efficient. Processes interact with other processes through operating system primitives, such as shared memory. And in comparison, a thread interacts with other threads using concurrent programming languages or libraries. For example, you can do thread mutex operations. Context switching. Context switching is much heavier for processes than threads because threads share a lot less information. And when you do a context switch, you only need to store a small amount of information for a thread. Next, we're going to talk about two important concepts, concurrency and parallelism. Concurrency refers to the fact that two or more threads are in progress simultaneously. So as we show in this example, we have two threads, and both of them are proceeding. That means both of them have started but not yet finished. Concurrent threads can execute on a single processor. That's why even on a single processor machine, we are able to execute pthread programs or thread-based programs because these threads will share the CPU resource. As we show in this example, the thread 1 and 2, they share one single processor. They take CPU cycles at different times. And this is what we call concurrency, so which again refers to the fact that we have threads that have started but not yet finished. They are proceeding in progress simultaneously. They may or may not be executed at the same time in any single cycle, but overall they are in progress together. Parallelism occurs when multiple threads execute simultaneously. Here we're referring to the real execution of these threads. So that means we do have execution resources, i.e. the cores or thread processors that can carry out the instructions from different threads. Parallel threads can execute on multiple processors or multiple cores. This is, as you can see, we have again two threads, and both threads are executed at the same time, and each one taking a different processor. If you want to design multi-threaded program or any parallel program, you have to be very careful. You want to start thinking of and resolving the hard questions at design phase. The following are the design concepts. We can use threading for functionality. We can use threading for performance. Within performance, we may choose to improve either turnaround time or the execution time of a single task, or we can choose to improve the throughput. And the way we design these parallel programs or multi-threaded programs is by decomposing the task. And we have essentially two ways to decompose a task of work. One is task decomposition, and the other is data decomposition. Threading for functionality. This essentially refers to that you can assign different threads to different functions done by the program, by the application. This is used in a case where the function overlap are rare, because you do want to have a clear partition of the task in the application if you want to do this functionalized multi-threading. It's easier to control the execution of concurrent functions within an application. Dependencies exist even without the direct interference between computations. So what we're trying to say here is, if you have a job you want to accomplish and you want to design a parallel program, if you can separate the subtasks from this overall task clearly, and then you have a chance to do functionalized multi-threading. This example, to build a house, we will involve different people. For example, bricklayer, carpenter, roofer, plumber, painter. And as you can see, each of them will have clearly distinct tasks. So you can use this distinction of the tasks because they have very rare interaction or overlap on the task. So you can do multi-threaded design by separating functions or assigning one function to a thread. One of the main reasons we want to design multi-threaded program is to improve the performance. Although it's hard, because we design programs normally when we think in a way that everything's serial, so it's very hard to design a parallel program. But the potential is big because we can improve on the performance in terms of turnaround time or throughput. Let's use this example. We have the postal service. There are different tasks involved in the postal service. We have post office branches. We have sorting machines, and we have people that deliver the letters, and also we have long distance transporters, planes or trucks. We can design a multi-threaded program for turnaround time. Threading for turnaround refers to completing a single job in the smallest amount of time possible. All right, we change to another example here. To setting up a dinner table, what we can do is we have one waiter organize the plates, and the other one folds and place napkins, and the other one do the decoration, and the other one place utensils, and then the last one place the glasses. Okay, so we can separate these tasks, and we can organize in a way that to reduce the turnaround time. The other performance metric could be throughput, and this refers to accomplish the most number of tasks in a fixed amount of time. I think in the beginning of the first lecture we explained the delay and throughput. Throughput refers to accomplish the max number of tasks in a fixed amount of time. So what we can do for this example, let's say we want to set up n banquet tables. So we're gonna have not one or two waiters. We're gonna have multiple waiters, an army of waiters to do these tasks all together. So some of them are doing the napkins, some of them are doing the utensils, some are doing flowers, etc. But the goal here is to organize them, have them busy all the time to finish n banquet tables in a fixed amount of time, and we try to maximize the n. So how do we decompose the task? We have two major strategies. One is to do the task decomposition, one is to do the data decomposition. For the task decomposition, we would want to assign different activities to different threads or different workers. This is very common in applications where you have independent functions you want to accomplish. For example, if you want to process network packets, you will probably let one worker thread to pull the packets from the interface card, the other one to look at the packet, to decide which network node is the next hop, and then the other thread to forward the packets out. The other way to decompose the task is to do data decomposition. This is a case where we have so-called data parallelism. Data parallelism refers to the fact that we are performing some tasks on a large amount of data. For example, in image processing case, we may do the same task on a pixel or on a group of pixels, a large number of group pixels. So in this case, the operation itself is the same, but you are dealing with a large amount of data. So what you can do is you're going to design your thread so each thread will perform the same function, but they will work on different data. That's what we call data decomposition. Task decomposition is to decomposing a program based on a function. So that's why it's also called functional decomposition. In design phase, if you choose to do task decomposition, you won't need to really analyze the work you want to accomplish. You will need to figure out what are the computationally intensive tasks involved in this work. And then we're going to try to first separate these subtasks so that they have little or no dependency. Because the less dependency you have, the less overhead you have among the threads. And then once you have this clear partition of the work, once you identified these different tasks, you can program your threads so that they each will take one of them. For some functions that they do have dependencies on other functions, you need to make sure that you have the proper synchronization mechanisms in place to avoid any race conditions. Here's a simple example of task decomposition. Consider a situation where you want to weed and mow your lawn. So you have two tasks. Okay? And these two tasks you can think about, they are independent. And you have two gardeners. And so the obvious the strategy is to assign one task to one gardener. So one is doing the weeding and one is doing the mowing the lawn. Data decomposition is for the case where you have large data sets. These data sets can be computed independently, and the needed computation among threads is known as data decomposition. So what we're trying to accomplish here is we're gonna create multiple threads, depends on how many cores you have, and we're gonna assign the same work, same functionality to these threads, but allocate different data for these different threads. The key points here is that the same independent operation is applied repeatedly to different data. For computation-intensive operations such as loops, these are oftentimes good candidates for data decomposition. Because think about loops, you're essentially doing the same thing on different parts of your array or matrix. So that's a good candidate for data decomposition. So we touched upon that which decomposition method to use. So you can do either one on the same work to solve the same problem, but probably one of them is better. It really depends on what kind of work you want to accomplish and the amount of data you're going to deal with. For example, here when you paint a wall, okay, if you can divide the task, chances are you're going to divide the wall into 2 halves or 4 quarters. If you have 2 persons, then each one take a half of the wall, and then if you have 4 persons, then each one takes a quarter of the wall. So that's a typical data decomposition. For the task decomposition, using example, grading the exam. So the exam paper has different questions in it, multiple choice, short answers, and circuit design. If you have different graders, then you can assign these different graders a problem to grade. And so they will work on different grading functions. And the exam paper will flow through these different graders. So like a pipeline. So this is the task decomposition. Or the other way is to do data decomposition. That is to say, you're going to have n graders, and every grader is going to grade every problem. So we're going to divide the exam papers to n portions. So each grader will take, say, 2 or 20 students from that class. So that's one way to do data decomposition.